Where am I? Let me check. That's weird. That is weird. NASA has sent tiny little rovers to Mars and put satellites into impossible orbits, but how do they know how to get there? Trying to navigate through space is like trying to find a needle in a haystack. However, you're also in the haystack and you're traveling at thousands of kilometers per second around a glowing ball. To solve this issue, we must look at how we position ourselves on our favorite planet, Earth. Let's say you're in Toronto, but you want to know where in Toronto you are. In order to find that out, your phone, right here, pings the 4 closest satellites. 1, 2, 3, 4. All 4 of these satellites are connected to a GPS system. These satellites have a specially designed orbit so that they always know where they are at any given moment. Let's take a look at one of these satellites. The satellite is sending your phone 2 key pieces of information when it is pinged: where it is and how far it is from your phone. It does this by measuring the time it takes for your signal to reach your phone. And by measuring the time and the speed, you can find the distance. For us, here are the positions of each satellite and their respective distances. The first satellite is at Halland's Point Beach, 10 centimeters away. The second satellite is at Medieval Times Diner and Tournament, 12.5 centimeters away. So now we know that your phone must lie somewhere in this area. The third satellite, Allen's Garden, is 8.5 centimeters away. And the fourth and final satellite is at Cherry Beach, 13.5 centimeters away. We know that our phone must be in all 4 of these circles. So the point that overlaps in each of these circles will be the point where our phone is, which is the CN Tower. Now, deep space positioning systems are a bit different, but in essence, they use the same system. The most common positioning system in deep space has a satellite and 2 tracking stations. The satellite will send 2 signals, each encoded with information about the frequency of the signal and the time that it was sent. On Earth, 2 ground stations will receive their respective signals and measure the time it took for the signals to arrive. Because we know that radio waves travel at the speed of light, we can find the distance between the satellite and the tracking station based off of this time. We can also easily measure the distance between the tracking stations on Earth, forming a triangle between the 2 stations and the satellite. With the law of cosine and the law of sine, we can find the angles of this triangle. Using these angles, a ground station can orientate itself to send commands and controls to satellites in deep space. This system is called delta differential one-way ranging. Furthermore, with information about the frequencies that the radio waves were sent at, we can compare it with the frequencies received and measure the speed of the satellite using Doppler shift, the same phenomenon that makes ambulance sound waves increase in pitch when the ambulance is moving towards you and vice versa. But these systems are foolproof for 3 main reasons. First of all is timing. These systems rely on precise clocks, however over time these clocks can slowly drift. Even atomic clocks, the ones used for deep space satellite missions, will slowly drift, and that is why these clocks are designed to not drift more than a millisecond in short-term missions. However, over longer periods, this drift can increase. Furthermore, special relativity can also cause these clocks to be out of sync, sometimes even by multiple seconds. And without precise timing, distancing and positioning systems will be horribly inaccurate. The second issue is signal distortion. Oftentimes, satellites do not have the capability of sending high-power radio waves over thousands of kilometers, so generally the signals that are received are very weak. With cosmic background radiation, Earth's ionosphere, the atmosphere, and many other factors, there are a dozen different ways that the signal can be distorted, meaning that ground stations will have to decode the likely jumbled up signal, which makes it even more difficult to receive the signal in the first place. The final major issue is positioning the Earth and other celestial bodies. 3D space is very hard to navigate as there are many angles and positions that need to be accounted for. Especially when celestial bodies are moving at hundreds of kilometers per second, it is very difficult to track everything. Ground stations and satellites rely on ephemeris data to keep track of this information. However, oftentimes this data is long and confusing, leaving room for error. Even one small miscalculation in the position of Earth, Mars, or any other celestial object will completely throw off the trajectory of a satellite. Alright, now that we're able to understand how satellites are able to position themselves, let's try to position ourselves using Nerf guns and balloons in my backyard. Before we get into the fun stuff, we must first understand the math behind it. Our system is the exact same system used by satellites in deep space. However, instead of using radio transmitters and receivers, we use Nerf guns, Nerf bullets as the radio waves, and balloons as the receiver. Oh, and by the way, for those of you that don't want to listen to this, feel free to skip ahead to this timestamp. To start us off, we first need to find the speed at which the bullet travels. Unlike the speed of light, which is constant, bullets travel at a wide range of speeds. So, to find it, I will shoot multiple bullets at a target and measure the time that it takes. Speed is just equal to distance over time. So if we have a known distance, and we know the time that it takes for a bullet to travel from here to here, we can just divide the distance by the time and derive the speed. Now, I shot 5 bullets. So I just added all 5 of the speeds that I calculated and divided it by 5 to get the average speed. If we were to recreate our system, we need to find this length and this length. To find these, we measure the time it takes for the bullet to go from here to here, and the time it takes for the bullet to go from here to here. And we can reverse our speed equation to get distance is equal to time multiplied by speed. And since we know the average speed from the previous calculations and the time from the recording, we can find the distance. Now, I'm going to label these side A, B, and C, and the angles opposite to them, capital A, capital B, and capital C. We already know sides A, B, and C, so now we have to find the angles using the law of cosine, which is A squared equals to B squared plus C squared minus 2BC times cosine of angle A. You can see that from this equation, we can find one angle using 3 sides. Reverse engineering this equation, we can get that angle A is equal to the inverse cosine of B squared plus C squared minus A squared over 2BC. With angle A, we can find angles B and C using the law of sine. Sine of angle A over side A is equal to sine of angle B over side B, which is equal to sine of angle C over side C. Reversing this equation, we can find that angle B is equal to the inverse sine of side B times the sine of angle A over side A, and C is equal to the inverse sine of side C times sine of angle A over side A. Now, to locate the position, we have to put our triangle on a graph. Now, we're going to set this tracking station as our origin. Now, to find the position of the satellite, we must first identify the elevation of line A and line B, which is just negative 90 plus angle B and 90 minus angle A. Now, the reason why the elevation is important is because the slope is equal to change in y over change in x. And since tan of theta is equal to opposite over adjacent, which is the exact same as change in y over change in x, tan of theta is also equal to the slope. Now, using the point-slope form of an equation, we can find the equation of both of these lines. We know this because we know the position of a tracking station, which is on the line. So we have a point, A and B, and we know the slope, which is just the tan of the elevation. And by combining these two things, we can get y minus b is equal to the tan of theta times x minus a. And we know that a and b are just the coordinates of the tracking station, and thus the position of our satellite. Okay, we're outside right now. I'm just setting up this camera. Alrighty then. How you guys doing? I actually figured out how to use the DJI mic, so now I can use it. How fun. Alright, here's what we're gonna do. Give me a second. For those of you that don't know, to measure speed, you need to know 2 things. The distance that something travels, and the time it takes to travel that thing. Now, here's what I'm gonna do to measure that. I have 2 balloons. First, we're gonna stick these 2 balloons over there on that fence. Let me see if you guys can see it. Yep, you guys can. We're gonna stick these 2 pieces of balloon These two balloons, no! No, come back, come back, come back. We're gonna stick these two balloons. Right. One here. No, my balloon. This game sucks. I hate balloons. Why are they so bad at this game? Okay, I'm gonna put one more piece of tape on just this balloon. Okay, that should work. Okay, now we gotta measure the distance. Luckily for me, I brought a tape measure. Okay, we made it to the end of the thing. So how many feet is this? This is 16 feet. Divided by 3. Okay, 5 meters. Right here is 5 meters. Right here. Drop. Okay, the measurements won't be 100% accurate. So, yeah. How about I just shoot it at the 5 meter mark? That would be so much easier. Because then I won't have to worry about inaccuracies in my measurements. And it'll be easier. 5 meters. Right here. Perfect. The chair is perfectly at 5 meters. Okay. Now let's fix the balloons. Okay. Let's see. Bring this back a bit. We're going to shoot from 5 meters, and I want to measure the time in Premiere Pro to see how long it takes for these bullets to travel. Hopefully I don't miss. Oh! Did you see that? Did you see that? Did you see that? Oh my God. Laser accuracy. Okay. Second one, baby. Oh, just a bit too low. Let's see. Too high. Okay. Let's try again. It hit the huh? Okay, that's weird. Okay, let's try again. Last bullet, and then I have to go retrieve them. Bring me home, baby. Oh my days. Okay, whatever, this is good. We got one of them, and we have a bunch of them inside of the wall. So we can just pluck them out. And I'll have Editor Max measure the speeds.
1 hour later.
Alrighty, so after measuring it in Premiere Pro, I have the thing in video here loading frame by frame. I shot 5 bullets, so I have 5 recordings. This one's much longer than it's supposed to be, but there's probably a glitch. I did the measurements, counted the seconds, and so these are the speeds of each bullet: 13.63, 11.11, 15, 15.789, and 12.5. I found the average, which is 13.6073897. You know, you gotta be precise. Alright, so here's the strategy. I'm gonna measure. Okay, I'm gonna go in front so you guys can see me. And I'm gonna grab my measuring tape. Right here, okay. So, the way satellites do this is they use a beam of light and they shoot it at a receiver. 2 ground stations. One here, one here. And you know the distance between those ground stations. Now, the laser shooting a beam of radio frequencies at both ground stations, they can measure the time it takes and thus the distance that it travels. This is because we know the speed of light. So if we have the speed and we have the time it takes, we can find the distance. Now, the speed of light's too fast, obviously, for me to measure it in my backyard. Like, I'm gonna need a much larger distance than just like a couple meters. So instead I'm using Nerf bullets. The transmitter is my gun, and the receivers are the balloons, which I'll aim at and shoot for. Hopefully I'll hit them. So here's the plan. I'm gonna measure 5 meters between these balloons, so I know that distance, and then I'm gonna stand at a random place in my backyard. Then I'm gonna shoot at both balloons, recording it and measuring the time that it takes for me to shoot it and it to hit the balloons, and then from that I can triangulate my exact position. Hopefully this works. Yeah, okay, let's go. All right, 5 meters, baby. All right, here's my tape measure. I'm gonna put it down at a random place. How about right here? So this is where our satellite is. It has absolutely no clue where it is. And it's our job to figure out. Okay, sorry for that sudden cut. I had to clear a bunch of storage because a big downside of using your phone to record a lot is that your phone doesn't have enough storage. I don't want to bring my computer out here. That's way too much effort. Okay, first target, that one. Let's go. Ready, set, fire. Oh, that was so close. It bounced off. It bounced off the ground and hit the wall. Did you guys see that? It's like very far there. It's like it on the wall. That's crazy. Okay, second bullet. Reloading. There we go. Bring it home, baby. Let me see that.
A few moments later.
Okay, now I'm gonna set up the camera at a different angle for this next shot because I gotta make sure this camera is my measuring. So I gotta make sure I get the proper measurements. To do that, gotta make sure the camera sees everything. Okay, let's go retrieve the bullets. So many creatures inside the dirt trying to eat me. Ah, so scary, so spooky. Any of you guys agree with this? This claim? Let me see. Okay, I still have storage, thank God. I do not want to delete more videos. At this point, the only videos that I'm deleting are old videos. However, I don't want to delete these videos. These are my memories, right? I'm sure many of you guys can resonate with that. Like, 3, 2, 1. Oh! Oh my God, the bullet bounced back. Let me see that, let me see that. Remarkable. Absolutely remarkable. Okay, I'm gonna tidy it up, and I'm gonna bring it inside, and we're gonna do some calculations using Premiere Pro and a lot of Desmos. Let's have some fun. Math time. After analyzing both of the shots, we get a triangle of this, where this will be our origin. Over here is where the satellite is, and over here is the other balloon. Now, all we gotta do is find this angle and find this angle. Alrighty, using the law of cosine for both of these angles, we were able to find that the angle of elevation here is negative 83 degrees about, and the angle of elevation here is 85 degrees. From this, we can derive two lines, and using that, we can find the exact position of our satellite. Yay! Alrighty, after doing some fun math, here is our location. These are our coordinates from our 0, 0. I don't know if these are 100% accurate. We'll have to check. There were probably a couple inaccuracies while doing the math, but when we check, we'll see. I think it's pretty close, though. All right, take 2. Okay, hold on. I still have the measuring tape from take 1. I don't want to move that. Or the first experiment, sorry. So what should I put there instead of that measuring tape? I need something that can distinguish itself. Maybe a bottle of Yop. This is nice. And I'm also cleaning up, so this is good. My parents will like this. Okay, let's throw this measuring tape at a random place. Ready, 3, 2, 1, drop. Right here. This is our ground 0. I'm gonna go blow up some balloons now. Ah, nice planes. Okay. Are you ready? No bullet in the chamber. Hello, everyone. This is our ground 0 now. Just a couple meters away. All right, let's get started. We have... Why do we only have 3 of the... Okay, I need to go find the other bullets. Hold on. Here's a bullet. And here's a bullet. Okay. I forgot to pick these 2 up. Okay. 3 of the 4 bullets. Or 5 bullets, actually. So we have all 5 bullets now. Let me just drop it in. Loading this gun. Alright. Let me just double check y'all can see. All right, y'all can see. Let me see. Okay, good enough. Maybe point it. Yeah, that's good. Okay. Ready, set, fire, fire. Oh, yeah. Beige, you see that? Oh my God, that was so fun. Okay, let's retrieve these bullets. I think I shot 3, right? 1, 2, and 3. Bro, this is so fun. You guys don't understand. I've always wanted to go to a shooting range and just shoot things. It's like doing this. Dream come true, man. This is awesome. Okay. Now this balloon. Okay, this balloon's a bit further now. So I'm just gonna orient the camera like that. Okay. All right. You guys should be able to see the top of my head. Okay. Do I have a bullet in? I do not. That's why I need to have a bullet in. All right, let's go. Ready, set, fire. First try. Oh my days. Oh my God. Oh my days. Oh my God. Canada military. If you need a marksman, hit me up. Did you guys see that? Goddamn. I'm literally LeBron James. Alrighty. Experiment number 2, something weird happened. I realized, after measuring the times, they both take 17 milliseconds. So they have the exact same thing, meaning this is an isosceles triangle. It's much easier to calculate, so the distance from each balloon is the exact same, 3.629, and each angle, or the angle of elevation from each tracking station is 42 point whatever that number is. And so let's put this into Desmo. Alrighty, we got the magic position. Here it is. This and this. Fancy numbers, fancy numbers. All right, we've done 2. It was super fun. I'm thinking we go for 3. Three experiments. So I'm gonna use this thing, to mark this position, then use a tape measure. Now I wanna do something behind here. So how about right here? There, yeah, pretty close to this and not so far from the other ones. Alrighty then, I'm gonna go blow up some balloons. Oh yeah, and for those of you wondering, I will be cleaning up. So don't worry, my chickens will not be eating food, basically. Not be eating plastic, sorry. Ready, down, set, hot. It hit the balloon, man. What are these balloons made of? Okay, goddamn. Twice in a row. So I might have to use Pythagorean to figure out the actual distance from the actual gun. So my shoulder height. Okay, shoulder height. Oh! The balloon's deflating. That's Do you guys hear this? There's a hole. Okay, that's crazy. So there was a puncture hole, but you know how if you poke something, like a balloon, pick a balloon or something, and there's tape over it, it will like not instantly pop. I think that's what happened. I hit the tape. Okay, that was cool. Oh my God, that was crazy. 2 in a row. Ready, down, set, hot. This one's difficult because it's far away. Oh, first try. Holy shoot. Holy shoot. Holy shoot. Holy shootin' my doody booty. Oh my God. Did you guys see that? Did you guys see that? Oh my days. I'm literally him. They don't call me LeBron James for no reason. They don't call me LeBron James. Okay, that's a wrap. Time to clean this up, bring this inside, and we're gonna do some math. Alrighty, after a whole lot of math and something, we have the third point, which is right here. the two black lines. I did some organization. Let's go check it out. All right, I brought in the cavalry, my dad. Let's get started. Okay. First up is that thing, that point, the third experiment, which I'm pretty sure should be, let's see, based off of these, with that being the origin, I think that's the, I actually don't know which one that is. Alright, you know what, let's just first measure, what's the one over here? Let's first measure this one, right, where's the tape measure? Right here, tape measure. So that tape measure will be, going back here, that tape measure should be this point, this blue point, which is 0.25 and 2.88. 2.88. Okay, let's try that. The tape measure is right here. I want to mark it with this little Lego thingy. Okay, because I need to use the tape measure, so might as well mark it with something else besides the tape measure. Okay, we gotta go to our point of origin over here. So let's see, first measurement is 0.25. Okay. So 0.25 meters this way. 0.25. Hey, let's see how close we were. We're actually pretty far. Okay. Let's see. We were, and the Lego figure is right about, where's the Lego figure? Right here. Okay. Let's mark down this point. Okay. Let's do the second one. This point. So this is the isosceles. So it's 0.81 and, no, this is the wrong one. Sorry, this one. 2.744 and 2.5. Okay. 2.744 and 2.5. Let me just roll this back in. Okay. 2.744 and 2.5. Right here. That's crazy. That's actually not that far. That's like, come closer. You see? So this one was for the yacht bottle. The yacht bottle's right here, and our measurement is right here. How awesome is that? Okay. Final one, which is this thing right here. All right, let's take a look. Final one will be the, come closer, this green point, which is 0.81 and 0.97. So 0.97 is, 0.81 is this way. Okay, that's pretty far away. All right, we got this one though. This is the one that I like most. You see how close this is? This is awesome. Now, I think the inaccuracy came because they're pretty far away from one another. The inaccuracy here is with the speed, I think. Because when we were finding the speed, it was very different because, you know, bullets are weird, drag is weird. All right, let me take it from here. Now, I think the area where the most inaccuracies derived from was when we were measuring the speed of a Nerf bullet. Because unlike the speed of light, which is always consistent, Nerf bullets just don't have this luxury. Sometimes they're really slow, sometimes they're really fast, and it's because there's like a million different factors that will influence how a Nerf bullet travels, right? The Nerf bullet's really lightweight, so it can suffer from drag. Sometimes the gun just doesn't work as well. So if I were to watch back the recordings, I'd see that sometimes the bullet will be traveling really fast, and sometimes the bullet will be traveling really slow. And because the speed of the bullet is inconsistent, and I can't generalize it with one number, and I think that's the area where I had the most inaccuracies. Now, obviously, real-world systems are much more accurate for a multitude of different reasons, and off the top of my head, I can list a few. First of all, they use the speed of light rather than Nerf bullets, which is always consistent. And also, they use atomic clocks to measure the time rather than eyeballing the time in Premiere Pro. Now, it's not like real-world systems are 100% accurate, right? Like I said before, they can suffer from clock drifting, they can suffer from background noise, they can suffer from the sheer math that it takes to actually position something in 3D space, and this is why space agencies like NASA and SpaceX work so hard to ensure that their systems are accurate, because one small miscalculation or one small error can completely throw off the trajectory of a mission. All in all, deep space positioning systems are crucial to interplanetary missions and exemplify human ingenuity and creativity in the face of adversity. Thank you.